All right, so today we are going to cover the innate immune system, which is the first part, the first line of defense when it comes to your body fighting off infections. So we went over an overview last week. We're going to cover it a little bit more detail today, and then we're going to do a concept map on it. So our plan for today is to know what the immune system is and how it works to fight infections, barriers to pathogens, and learn about specialized cells that protect our bodies. So we're going to start with the non-specific part of your immune system. Okay, so this part is not going to go after specific types of pathogens. This one is just going to be barriers that cover all pathogens in general. And then tomorrow and Thursday, we will cover the adaptive immune system, which is those T cells and B cells that we briefly talked about last week. So we will cover those starting tomorrow. So today we're talking about the first line of defense, which are barriers. And there are three basic kinds of barriers. So your immune system, remember, consists of complex networks of cells, tissues, and organs. It functions to defend the body against harmful pathogens and foreign substances, and it plays a crucial role in maintaining your overall health and preventing disease. So of all the systems in the body, this one is one of the most important next to your circulatory system because it's basically helping you stay healthy. So, oops, I went through on my, sorry. So the innate immune system includes physical barriers, chemical barriers, and biological barriers. And I will post this presentation in the content folder so you have access to this starting this week. So we're going to talk about each one of these different types of barriers. So the first one is your physical barriers. And these are mechanical barriers that block pathogens from entering your body. And we talked a little bit about these last week. You have your skin, you have your mucous membranes, your cilia, and your hair. Who remembers what cilia are? What are cilia? Anybody remember what cilia are? I know that's kind of a funny word. Nobody knows? Nobody remembers? So cilia are little tiny hairs. So little tiny hairs that are found all around your bodies. They can be found in your ears. They can be found in your nose, but they basically block dirt from entering any kind of a orbit that's in your body. So you've even got your eyelashes that kind of protect things from getting into your eyes. So little tiny hairs are what are called cilia. All right, so I know we watched this last week, but we're going to watch it again, but it's how mucous membranes keep your body healthy. We'll be having a question on this on your final exam, so make sure you're paying attention. Let me know if you can hear this.
If you've got a cold, mucus is hard to miss. But what is it? And what does it do besides making you miserable? Your body produces more than 1 liter of mucus every day. And all the wet surfaces of your body that are not covered by skin, like your eyes, nose, mouth, lungs, and stomach, get a liberal coating. That's why they're known as mucous membranes. Mucus plays lots of roles in your body. It keeps delicate tissues from drying out and cracking, which would expose them to infection. It lubricates your eyes so you can blink. It protects your stomach lining from acid. It neutralizes threats by removing or trapping substances that could make you sick. And finally, it houses and keeps your body's trillions of bacterial inhabitants, your microbiota, under control. Mucus contains lots of different compounds, including proteins, fats, and salts. But a key component of mucus versatility is a set of proteins called mucins. Mucins are the primary large molecules in mucus and are essential for giving mucus its slippery feel. They belong to a class of proteins called glycoproteins. which are built out of both amino acids and sugars. In mucin, long chains of sugars are attached to specific amino acids in the protein backbone. The hydrophilic sugar chains help mucin dissolve in your body's watery fluids. Mucus, which is up to 90% water, stays hydrated thanks to these sugar chains. Some of these mucins can interact with other mucin molecules to create a complex network that establishes a barrier against pathogens and other invaders. That's why mucus is the body's first line of defense against foreign objects like bacteria and dust. It's continuously produced to clear them from the respiratory tract, like a slimy conveyor belt. This keeps bacteria from getting a solid purchase on delicate lung tissue, or making it to the bloodstream, where they could cause a major infection. Many of those harmful bacteria also cause diseases when they cluster into slimy growths called biofilms. But mucus contains mucins, antimicrobial peptides, antibodies, and even bacteria-hungry viruses called bacteriophages that all work together to prevent biofilms from forming. If microbes do become harmful and you get sick, the body ramps up mucus production to try to quickly flush out the offenders, and the immune system floods your mucus with extra white blood cells. In fact, the greenish mucus often associated with infections gets its color from an enzyme produced by those white blood cells. This multi-pronged approach to bacterial management is one of the main reasons why we're not sick all the time. Even though mucus protects against the infectious bacteria, the vast majority of your body's bacterial tenants are not harmful, and many are actually beneficial. That's particularly true when they live in mucus, where they can perform important functions like synthesizing vitamins, suppressing harmful inflammation, and controlling the growth of more harmful species. So even though you probably associate mucus with being ill, it's really helping you stay healthy. Sure, it might seem gross, but can you think of any other substance that can lubricate, keep your body clean, fight infection, and domesticate a teeming bacterial population? Nope, just mucus.
Okay, so I have two questions for you that I want you to answer in the chat box for me. And I want to hear from everybody. So did anybody catch how much mucus do we create a day? Anybody catch that? I want to hear from everybody. Put it in the chat box. What do you think? How much mucus do we produce every day? Good, Jana. Come on, everybody. Landon, Michelle, Michael, Kayla, Ariana. How much mucus do we produce a day? Jana, I think you're the only one in class today. Come on, everybody. Ariana, Michael, Michelle, Landon. Put a number in the chat box. What is your guess? Thank you, Ariana. Landon, that's a lot. All right, so we produce about 1 liter of mucus every day. And did anybody catch, and I want to hear from everybody, how do we know if we're actually sick based on mucus? What is your best guess from the video? How do we know? Nobody caught that? Yeah. So when you're sick, your mucus is a different color, and that's because of the enzymes and the bacteria and the chemicals that they're secreting when they're breaking down the bad stuff. And so when you're sick, your mucus will be kind of a greenish yellowy color. And if you're not sick, then it's kind of a white, clear, fluidy color. So like if you feel like you're sick or you think you're sick, but your mucus is white, then it's probably just allergies. But if you feel like you're sick and you think you're sick and your mucus is yellow or green, then that means that you have an infection and you probably need to go see a doctor. So that's really important information that you need to know moving forward in life. You need to know when you're sick and when you're not sick. So there are chemical barriers that are found in our skin, in our sweat, in our tears, in our saliva, semen, and stomach acid. And chemical barriers are proteins that destroy pathogens at the body surface. You know, your body makes proteins for all different kinds of stuff. Those proteins are made in your ribosomes, in your cells, and a lot of your cells make proteins, and they have different jobs. They're like chemical signalers. They're used to fight infections. They're used to build other things. So proteins have a huge job, and there's a lot of different kinds. But there are some that destroy pathogens in your body. And so enzymes are an example of a protein. Lysosomes, which was in your reading material from last week, which are found in sweat, mucus, tears, and saliva. Those lysosomes break down or kill pathogens by breaking up their cell walls. And so those specific enzymes, which are known to speed up chemical reactions, that's what enzymes do. The ones that are the main part of your immune system are called lysosomes. And you will probably see those on your test, hint, hint. All right. So those are the chemical barriers. Then we have the biological barriers. These involve living organisms that compete with pathogens. So these are like good bacteria fighting with bad bacteria. And you have good bacteria in your body. You have good viruses in your body called bacteriophages, which kind of ingest and engulf bad stuff. And it's important to have those in your body. And whenever you take like an antibiotic, they always recommend that you take a probiotic with it, so that even though the antibiotic is going to kill off all the bacteria in your body, the probiotics will put good bacteria back in your body to help with your digestion and stuff like that. So these can be bacteria that are found on your skin. They can be found in your urinary tract. They can be found in your stomach acid. Those are bacteria that can withstand really strong acidic environments. They're found in your genitals. So human skin is covered by millions of bacteria. Your skin is always covered with bacteria. And that's why they always say it's good for you to wash your hands after you go to the bathroom. It's not just because you might have gotten urine or, you know, anything like that on your hands while you're going to the bathroom, but you generate bacteria on your hands all throughout the day. So if you wash them a few times a day, especially after you go to the bathroom, you can keep yourself a lot healthier. So most of these bacteria are helpful, or at least not harmful. So there's some bacteria that are living in you that are neither helpful nor harmful. Okay, they're just kind of hitching a ride. They're living off of your, your skin cells. They're living off of whatever it is that you're digesting, but they're not hurting you. Okay, so it's only the bacteria that are harmful or hurtful that will make you sick, and that's because they reproduce very quickly, especially if you have like a low immune function, like your immune system doesn't really work properly. All right, so we are going to watch this crash course on the innate defenses. So if somebody can give me a thumbs up and let me know if you can hear this, that would be great. And then we're going to do that concept map.
You may not know it, but your body is engaged in a never-ending battle. You are literally covered in staph and strep and E. coli and all sorts of dubious characters that are intent on using you and your body's many resources to feed themselves, find shelter, and reproduce as much as they want. And hey, we all gotta make a living. But it is not your job to give these guys a free lunch. So your body has developed a 3-part policy toward these shady customers, and its enforcement is handled by your immune system. The immune system is different from all the other systems we've talked about this year in that it's not a specific tissue, organ, system kind of system. Instead, it involves a whole bunch of different tissue groups, organ systems, and specialized but widely distributed defense cells. Together, this league of extraordinary substances joins forces to perform all of the defense functions your body depends on to keep you alive in an incredibly germy world. And the first line of defense in this never-ending battle, that's your innate or non-specific defense system. Like your average frontline soldier, it's prepared to immediately engage with anyone suspicious, and it mostly includes stuff we were born with, like the external barricades of your skin and mucous membranes, and internal defenses like phagocytes, antimicrobial proteins, and other attack cells. But some enemies must be fought with special forces, and here your body can deploy your adaptive or specific defense system, which is more like your SEAL Team 6. It takes more time to call in, but it's specially designed to go after specific targets, and it keeps files on those bad guys so it knows how to handle them next time around. But today we're going to focus on your innate system and look at how it uses an arsenal of physical and chemical barriers, killer cells, and even fever to keep you healthy, proving that sometimes the symptoms we associate with illness are actually the signs that we're healing. Just because something is simple doesn't mean that it can't be elegant. I mean, your body is capable of some incredibly sophisticated things, including defending itself from infection. But occasionally, there's something to be said for brute force. And a lot of your innate immune system's functions aren't exactly subtle. For example, your body's very first line of defense is a simple physical barrier. And it works. Like a wall around a fortress, your skin does a fantastic job of keeping out all manner of malevolent microorganisms. As long as that tough, keratinized epithelial membrane doesn't get torn open or busted up too much, you could probably make snowballs out of raw sewage and still be all right. Although, no. Your many mucous membranes also provide a handy physical barrier. You'll remember that they line any cavity that opens up into the germy outside world, including the respiratory, digestive, urinary, and reproductive tracts. Not only do your skin and mucosa supply simple physical protection, they also pack some serious chemical weaponry. Eat some questionable leftovers for lunch? Don't worry, your stomach is literally filled with acid, so you probably are covered. Walk face first into your coworker's nasty sneeze cloud? No worries, your nasal passages can whip up a tissue box worth of sticky mucus to help trap viruses before they enter your lungs. You've also got bacteria-fighting enzymes in your saliva and lacrimal eye fluid, and peptides called defensins in your skin and membranes that help keep bacteria and fungi from setting up shop around inflamed or scraped skin. Which, no matter how careful you are, you're gonna get one way or another. Maybe you shave with a dull blade, or you just brush your teeth too hard, and don't get me started about the dangers of bagel cutting. So when you've breached that first simple line of defense, it's time to call on your second line of internal innate defenses. This is where your body starts pulling strategic maneuvers like firing up a fever, releasing chemical signals, causing inflammation, or other defensive tactics that help identify and attack infectious invaders. Some of the first defensive cells on the scene are your phagocytes. Their name literally means to eat, and like Pac-Man, they indiscriminately chase down intruders and gobble them up. And they come in a few different varieties. First, you got neutrophils, which are the most abundant type of your white blood cells. They kind of self-destruct after devouring a pathogen, and in fact, you've probably seen piles of their little dead bodies, because that's what pus is made of. But the bigger, tougher phagocytes are the macrophages. They're derived from monocyte white blood cells that have moved out of the bloodstream to occupy tissues. And some are free types that patrol tissues looking for creepers, while others are fixed, attached to fibers in specific organs, devouring anything suspicious that passes by. So when a macrophage, in say the finger I just cut slicing a bagel, sees a new bacterium coming along, it snares it using cytoplasmic extensions, reels it in, completely engulfs it, and essentially digests it and spits the rest out. And unlike neutrophils, it can do this over and over again, like a boss. But not all your defense cells are phagocytic. You've also got cells with what is by far the awesomest name of any cell in the body, the natural killer cells. You can call them NK cells if you want to, but like, why would you do that? Anyway, these tiny assassins patrol your blood and lymph looking for abnormal cells and are unique in that they can kill your own cells if they are infected with viruses or have become cancerous. How can they tell? A normal, healthy human cell contains a special protein on its surface called MHC1, or major histocompatibility complex. But if it's infected, it stops making that protein. And if an NK cell detects a defective cell, it doesn't swallow it whole like a macrophage. It pokes it with an enzyme that triggers apoptosis, or programmed cell death. Pretty awesome. So those are some ways your innate immune cells handle their enemies, but how do they know where to look in the first place? So let's talk strategery. So say you're in a banana factory and you slip on a banana peel and you scrape your knees. Your outer fortress has been breached and the pathogens are just flooding in like orcs through Helm's Deep. Banana factories are very dirty places. Now your body wants to contain the spread of pathogens, clean up the mess, and get healing as quickly as possible. So it cues up your inflammatory response. This is basically an internal fire alarm, only it uses chemicals instead of sirens to get the message across, and instead of smoke and fire, you sense redness, swelling, heat, and pain. For example, in the event of injury, specialized mast cells in your connective tissue send out histamine molecules, and histamine is great at calling in the cavalry. For one thing, it causes vasodilation, which creates redness and heat at the site of the injury. Now, those things might freak you out a little, but they're actually signs of healing. The increased temperature, for example, ratchets up the cell's metabolic rate so they can repair themselves faster. Meanwhile, histamines and other inflammatory chemicals also increase the permeability of blood vessels, causing nearby capillaries to release protein-rich fluids. This causes swelling, which again is actually a good thing because that leaked protein helps clot blood and form scabs, while the lymphatic system sucks up and filters that extra fluid, cleaning it up before putting it back into your bloodstream. And of course, like chum to sharks, an inflamed knee is also going to attract a bunch of local phagocytes, which find it easier to escape your now leaky capillaries, and lymphocytes that are also flowing freely, helping to destroy pathogens while also cleaning up dead cell wreckage. And don't forget, during all of this, the neutrophils have been doing their best, but they were the first wave to arrive, so by this time they're starting to die in heaps. They're triggered when the injured knee skin cells release chemicals that begin leukocytosis, the release of neutrophils from the bone marrow, where they're made, into the bloodstream. To attract the neutrophils to the damaged area, inflamed endothelial cells in the capillaries send out chemicals that act like homing devices. And when the neutrophils arrive, they cling to the capillary walls near the injury, flatten themselves out, and squeeze through the vessel walls to get to work. Your big monocytes eventually roll up to the battle and transform into hungry macrophages, replacing the first line of now dead neutrophils and basically just eating up any lingering enemies and then cleaning up the carnage. Now, all this works pretty well in most circumstances, but you may have noticed with a more major injury or an especially nasty virus or infection, sometimes your local troops get overrun. When white blood cells and macrophages run into more foreign invaders than they can handle, they let loose pyrogen chemicals that tap the hypothalamus and raise your body's thermostat, calling in a systemic fever to burn everything. The resulting temperature rise increases the metabolism of your cells so they can heal faster, and it also tells the liver and spleen to hold on to all of their iron and zinc so those things can't contribute to bacterial growth. But even then, sometimes you find yourself facing a more formidable foe. That's when you call in the specialists, your adaptive immune defenses. And to learn exactly how they save the day, You have to watch next time. But for now, you learn that your immune system's responses begin with physical barriers like skin and mucous membranes, and when they're not enough, there are your phagocytes, the neutrophils and macrophages. You also learned about natural killer cells and the inflammatory response, and watched as all of these elements saved the day when you slipped on a banana.
Thank you. All right, so you're going to go in and you're just going to fill this in. So we have our innate immune system. And as he said, there's two different immune systems. There's the innate immune system, which includes all these barriers. And then there is the adaptive immune system, which is what we're going to talk about later this week. So the innate immune system consists of physical barriers. Their job is to block pathogens from entering the body, and that's your skin, mucous membranes, cilia, and hair. Your chemical barriers are all those other things that he was talking about, the neutrophils, the macrophages, the histamines, all that kind of stuff. These are proteins that destroy pathogens at the body's surface. They can be found in your skin enzymes, sweat, tears, saliva, semen, stomach acid. Then your biological barriers, the living organisms that compete with pathogens, and those include bacteria in or on your skin, urinary tract, stomach, and genitals. And so this concept map is what you're going to want to study for your final exam on the innate immune system. So go ahead and get started filling that out. Once you finish, go ahead and submit it, and then turn in the assignment page in Unit 11 of your class, okay? If you understand the directions, go ahead and give me a little thumbs up so I know you understand. Thank you. Thank you, Landon. Thank you, Jericho. Thank you, Jana. Thank you, Talia. Thank you, Michelle. Gage, you need to click on that link in the chat box and fill out that concept map. And then submit your assignment page within the class.